Hello and welcome to the KIM-1 Corner Part 7. In this episode, we'll be looking at this board that I showed you in the previous episode. Now, by the magic of time travel, here's the board all made up. Now, you may have noticed from the writing underneath, it describes what this actually is. It's a CPU card. We've got an expansion card up here. We've got the new comms port. And we've got the memory card, and everything's now running off of these ROMs up here. So we don't really need the ROM that's on there. We're using a little bit of RAM off that, and there's some RAM on there we're using. So on the KIM-1, all we're really using is the 6502 up here. This is the bottom 1K of RAM. We're using that. So the little bit of RAM on these two we're still using, and the clock generation up here. So we're not actually using the keyboard or any of this anymore, or any of the tape loading stuff. So I thought, well, what about the people who haven't actually got a KIM-1? No, they couldn't build this. So why not build a board that's got CPU on it, this RAM at the bottom, the bit of RAM that's in these chips, and the clock generation up there, and plug that in. So that's what I've done. And you end up with this setup. You've got the comms card at the back, got the memory card at the front, and with the new card, we plug that in. There we go, we've got a whole system that can run all the KIM software. So memory at the front, CPU in the middle, and comms at the back. They can be in any order, it doesn't matter. The bus at the bottom is just parallel all the way across. See on its side, see it a bit better. So that's a standalone computer that runs all the KIM software now. So for those of you who haven't got a KIM-1, you could build this. So here we have the CPU card. On this we've got 6502, same as on the KIM. Now this RAM chip here, this is a 2K RAM chip, and that will be doing the bottom 1K plus the other 128 bytes that's in the two Riot chips. Now I have included a ROM chip option on here, and that is addressed for the Riot chip ROMs, but you don't need that at all. That's just, I don't know, somewhere else you can put some more data, or even actually this ROM chip at the moment has actually got the code from the two Riot chips on it, even though some of it won't actually work. And this here is just some decoding logic for the addressing, because this one you got to... Let's get the other card, bring it over. So the RAM is K0 and K5. It's got to cover both of those. And actually when it does K5, it's only doing the top 128 bytes, the K5, so that we can use the other addresses within the K5 range for the hardware, because the comms card sits there. And I've got another card coming up which will sit in there as well. Now this is ROMs K6 and K7. If you didn't use this, you could use those addresses for something else if you wanted. If you notice down here, this is the reset button, so we'll be needing that. And just a simple capacitor resistor network here for the reset, and that goes through a SMIT trigger. These numbers on the board, they're wrong. That's a 74LS14, and this one up here is a, what have we got on there? That's a 00. I've corrected it on the new version of the Gerbers for this. So it's got the right numbers. I mean, they're the right chips and the circuit's all correct. It's just the labelling was wrong. This one has to be a SMIT trigger. Originally, the first version of this, you notice this is version 3. Well, version 1 had exactly the same oscillator circuit as the KIM-1. I thought I'd copy it exactly the same. But you just can't get 1 megahertz crystals anywhere. So I ended up buying one of these because I thought, well, I could get a 4 meg and then do dividers and what have you. Well, by the time I'd done that, I might as well just stick this in. So I bought one of them. That was, well, I think it was about £3 or £4 for one of them. But you get a nice crisp clock signal out of there. So we'll have a little look at the circuit of this, although it's pretty much the same as the KIM. Just this decoding is a little bit different. So here we have the circuit diagram with the edge connector and reset circuit, and here's the 6502 and the RAM chip and the ROM chip and some other circuitry. There's the edge connector with the 60 pins on it, and so that's feeding up onto the bus up here. And here we got the reset circuit. So that's the push button for the reset, and a simple RC circuit going on to a couple of Smith triggers to give us a nice clean reset signal, which will be coming back out of this pin. Remember, this socket now is an out, mostly going out. We're feeding the signals out. This will be emulating the KIM. I'll put another socket here so you can do an external reset if you wished. And this is that oscillator little tin can, providing the clock straight into the phase 0 input of the 6502. So that's the 6502. And that'll be sending all the signals out of these buses. And this bit of logic here, this is straight off the KIM board. So you've got your phase 2 comes out and your read-write signal comes out. And through a bit of combination, etc., you end up with not phase 2. Phase 2 got the RAM read-write, which is sort of linked in with the phase 2. So the RAM read-write doesn't actually come on until the phase 2 clock has come on. I think that's to stop spurious noise getting onto the RAM chips while you're on phase 1. And then you got your a not read-write and an ordinary read-write. So putting it through these ICs buffers it, so you get a bit of a stronger signal for these signals going out to the bus and other chips. You're not loading up the processor. So this not read-write and not phase 2 come in handy later. These are just the capacitors, decoupling capacitors that we put around the board. These 3 resistors are pull-ups for the ready, non-maskable interrupt and the ordinary interrupt. So make sure they're pulled up to VCC. So you pull them down to get your interrupts. And here we've got the RAM chip. Now we've got a special chip select for that, which we'll go through in a moment. Then the RAM read-write comes in, and there's that chip select again. So basically, not chip select and not output enable are linked together. As you can see on the ROM side here, they're all linked here. That just shows them going onto the bus, because the ROM's got its own little bit of logic here. We just look at the ROM logic before we go to the RAM logic. We've got K6 or K7, we want that to come on. So by using a NAND, so basically those two are all together, then the addresses come in, and we've got A10 coming in here because this is a 2K ROM chip, so it'll be doing both K6 and K7s, because remember each one of those is 1K and this is a 2K ROM. We bring all the addresses in to select that. And the data buses. These some spare NAND gates. Always tie your inputs down to 0 volts to stop them oscillating. Otherwise you can damage the chip and cause all sorts of noise everywhere. Okay, so this RAM chip up here needs to have 2 chip selects basically, but have them all together, like the ROM chip did here. But this has got to be a bit more careful on this, because that one's just doing 2 1K blocks. This has got to do a 1K block plus a partial block. So down here we'll have K0, which is the bottom 1K, so we want that signal, so that's these addresses. Or we want the top 128 bytes of the K5 zone. Now K5 is a 1K block, and if we chop that into 8 pieces, that gives us 128 bytes per piece, which is exactly what we want. If we use the K5 to enable the 74138, it's with these 2 enables here, so that enables a chip when we're on K5. So it's going to decode the next addresses down from that. So for the bottom 1K, you'll have addresses 0 to 9. So if we decode the top 3 of them, it's A9, 8 and 7. These outputs here, each one of these outputs will represent 128 bytes of memory. This will be the bottom 128 bytes of K5, and that's the next 128 and so forth, up to the top 128 bytes coming out of Y7. So that signal there is K5, but just the top 128 bytes. It's coming in here, so we want that signal or this signal. So that address to there. And if you look on the memory map of the KIM-1, you'll see that those addresses is what I call the KIM RAM. Actually, they've got it written down as KIM. They've got KIM RAM and application RAM. It's just a spare chunk of RAM that gets used by the KIM software, so we need it. Coming out of here, this is the inverted signals. We just invert it again to give us that. We're using the AND gates again as like OR gates. Oops. Hey, what am I doing? as we did up here. So we're doing it down here, and then that signal coming back round is chip select 01. It's does both the bottom 1K plus this extra little bit here. So when you're actually in the RAM, so we've got K0 going into A10, so that when K0 selected, A10 is 0, and we're accessing the bottom 1K of this RAM chip with these addresses here. So that's normal. And then when K0 is not selected, we'll have a 1 here. So we're on the top 1K of RAM within this IC, and we're relying then on this chip select signal here to only come on when it is the top 128 bytes. So there's a chunk of, there's about 800 and something bytes of this IC are not actually used. We can't address them. But that's okay, this is just simulating the RAM that's on the KIM board. So there we have the CPU card. That's all the bits from the KIM that we were still using, apart from the tape and the onboard teletype. We don't need the onboard teletype because we've now got the teletype card. So for those of you without a KIM-1, you could have this processor card, teletype card, and the other memory card. You need the other memory card because it's the only way of decoding the top addresses for the reset vector to get it going, unless you was to modify this in some way, add another bit in here so this looks at the top addresses and just have you that 2K of ROM running there, but you'd be limiting yourself quite a lot. So you need the RAM card really to be able to do anything. You may recall in the previous episode I mentioned about having a lot of grief with this card, having trouble with the binary coded decimal arithmetic coming on. This just wasn't working. Well, some parts would work, and then when I go to select like the basic, that had stopped working. And I couldn't understand why, and I went through all the software. I was pulling my hair out for nearly a week, doing things, rewriting ROMs, etc. And at one stage I thought maybe it was these sockets. I had trouble with sockets before. So the sockets I had in here, I've written out. I basically rebuilt the whole board. While trying to take the old sockets out here, I damaged the board, so I took everything apart, and this is a whole new one to build. I managed to transfer most of the components over. And oh yes, you can see there's a wire link up there because those pull-up resistors, I'll pull them down instead of up, so a little bodge there. But that's again fixed on the version 4 board, which is the Gerber I'll put up. And also this capacitor down here, that's, oh, can you see it? That's in a really awkward place. I've moved that up as well. I don't know why it is. When you're running on the KIM itself, then the binary coded decimal flag gets set off. But when you're running this board, when it starts up, it's set on for some reason. Hence, as I showed you before, I went through the software, turning it off in lots of places. As soon as I turned that off, everything started working right, as in the basic wasn't working because it was doing some calculated offsets for vectors, etc. And it was going to the wrong place because it couldn't multiply. I ended up with my logic analyzer on this, looking through the instructions. I ran it on the KIM, and then I ran it on this board, and I compared the two together, going through instruction by instruction, and I eventually spotted, after about 1,000 instructions, where it went off in a different direction. And I looked at the values coming out onto the bus, and it did the calculation different. I found out exactly in the software where it was going wrong. Then I wrote a little bit of test code and found out that it wasn't adding up right. And I happened to notice that it was doing decimal adding up rather than binary. And that put me on to the fact about that bit. I didn't know anything about that bit until I had that problem. And that's why it took me like a week to find another board. That was a nasty one. So looking at the actual monitor program, very first thing there is clear that decimal mode. I actually done a complete rebuild of the processor cards just because that one bit. So when you start up, turn that bit off. Don't assume that it's going to be okay. So when they built the original KIM-1, they made that assumption, and for some reason it came up okay. I can't see anything in the circuitry to force it to come up that way. Maybe it's just the way the power supply switches on. Maybe the KIM-1 comes on softer. There's a difference in the reset circuit, so maybe their reset holds off for a while until the power supply is fully on, then does a reset and clears it. Although I always press the reset button. Yeah, it could be something to do with it, I guess. Because I did spend a lot of time looking at the reset circuit as well. Pop back to the circuit diagram. This reset circuit here is quite basic. It's just a resistor charging the capacitor. Let's swap to the other window so we can zoom in. We just, when you press the reset, short this capacitor out so there's 0 volts there, and this all goes, that's 0, that goes to 1, so it goes to 0, so that pulls the reset down. And then when you release the button, that charges back up, fills the capacitor back up, and when you reach a certain voltage, this turns on. Well, what I had to start with is I didn't have SMIC triggers in here, just got the wrong chip, I wasn't thinking. And therefore this restart was really messy, it was bouncing on and off and all over the place. I had the scope on there. And when I put the SMIC triggers in, bang, it comes on lovely and clean. Although that still didn't fix the issue. Remember, they've got to be SMIC triggers. That's a 74LS14. Oh, we plug this in and we power this up as if to say we're running KIM-1, and we'll see how it goes. We press the reset button, and let's run up Putty and see what we got. Okay, so we run up Putty, probably COM3, I'll guess without looking it up. Normally is. And there we go. Let's press the reset again. There we go. The KIM's running with all the usual stuff in there. So if you go to like EO65 space, there we go, and show us what's in there. And Control J, take us back again. So we are, let's back up where we were for the basics. We go from there. Ask us memory size, terminal width, and there we go. We're in basic again. There we go. So you're all running. And Control C takes a while to break. There we go. If the basic program's running quickly, the Control C takes a while to break in. It's all working. So that's as if you're running it on a KIM, but we're not. We actually just got that one board running on its own, which is just sitting there, all running nicely. So if you want to build your own standalone computer, there you go. As I say, I'm going to build some more cards for this. The comms card here, you could actually put 2 of them in, but you need to update the software. In the next episode, I'll be going through some of the modifications I've made to the monitor ROM. We're actually running a new monitor ROM now, but I want to save those bits for the next video so you can see the sort of things I've been doing to it. And as I say, we're going to add another card in the video after that. I've got to build it yet and get it working. So don't forget to like and subscribe. And this video is a bit shorter than the last one, but hopefully it will enable some of you to build your own. I'll put all the Gerber files up so that you can build your own balls if you wish. And I'll put the pictures of the circuit diagrams up as well so you can see what goes where. So I hope to see you in the next episode where we'll be expanding the monitor ROM.